Hello students, welcome back to next lecture in our course Environmental Modeling and Simulation. In today's lecture we are going to continue our discussion on the epidemic model, the very simple model that we discussed in the last lecture, where we took a three-dimensional model that had the dimensions of healthy population, sick population and the population that died due to the disease, and we reduced it to a one-dimensional model and then we non-dimensionalized it. So, now we are going to look at the non-dimensionalized version of our epidemic model and we are going to see how the system behaves. And I am going to do this in two ways. The first way is the usual way that you are more familiar with, which is we are trying to draw a face portrait. The second way that I am going to do is the Nullcline method. So, once previously we have used the Nullcline method in this course and we are going to reuse it. Hopefully, it will be a good revision of how to use the Nullcline method. Alright, let us get started. So, what was our model? The epidemic model, the reduced 1D model. We had du by d tau is equal to a minus bu minus e to the power minus u. So, here we have a line and here we have a curve. So, just to remember, a was equal to n by x naught, this is very important, and b was equal to, okay. So, we already established in the previous lecture that a has to be greater than 1 because the total population will be more than the initial number of healthy people before the infection started spreading. And then we also should notice that b here should always be greater than 0, should always be positive. So, now let us go ahead and let us draw the face portrait. I hope you remember that for 1D face portraits, on y axis we will put the rate, which is du by d tau, and on x axis we will put the variable u. So, we have a line and we have a curve, their intersection will give us fixed points if any. A is more than 1, so let us say this is 1 here, A is more than 1, so A is somewhere here, okay. So, and B will always be positive, so A minus Bu, what it means is that since B is always positive, let us say B is like 2, so we have A minus 2U. So, this line is always going to be a downwards facing line, it is always going to be a downward facing line, A minus Bu. Now, if you look at our curve E minus u, when u is equal to 0, which is basically we are on the y axis, E minus Eu will be equal to E minus 0, which is 1, the highest value here, 1. And as we proceed further, it is going to reduce until when it reaches infinity, it will be equal to 0. So, let me redraw this so that it is easier to interpret this curve. Slowly this value is going to reduce, the curve is going to reduce. So, if you look at here in this situation, right now the line and the curve will intersect after a very long, some high value of u. So, this is your fixed point, u star. Now, let us find out the stability of this fixed point. On left side of the fixed point, let me make a circle here to show we are talking about a fixed point. On the left side of the fixed point, the line is above the curve. The line is above the curve. So, du by d tau is going to be positive. So, u is going to increase. So, the flow will be towards plus infinity towards the right side. On the right side of the fixed point, the line is below the curve. The line is below the curve. So, du by d tau is going to be negative. The flow is going to be towards minus infinity towards left side. So, you see that this is an attractor. So, basically when the infection spreads, when it starts spreading, what this model is right away telling me, if my u initial is less than u fixed point, then the disease is going to spread and claim some casualties before it stops. If initially, well, you know, u never goes back. So, we are more interested in what happens when we start with no casualty and then move on to some number of casualties. Let us see something very interesting. Let us vary A and B. If we start with the high A, so remember in the last lecture I told you that one example of A could be 1000 by 999, and another, let's make it easy for us, 1000 by 500. So half of the population is infected right at the first instant of the outbreak. In second case, only one person or one unit of people are infected. So here this is approximately equal to 1, and this is equal to 0.5, the half. So here this is approximately equal to 1, and here it is equal to 2. So we know that if we start with, let's say, nearly 1, very close to 1, we keep the B constant. We are varying A. Let me write it here. We are varying A. So we are starting with very few number, proportionally a few number of initial sick people. Then let me use another color for this. So very close to 1, then keeping the B constant, the line keeping the B constant, the fixed point moves to the left, and again it's a stable fixed point. So if we start with less number of initially sick people, we can reduce the overall casualties. However, because remember U is giving me an idea of the casualty, so let's use another color now. However, if I use A is equal to 2, which is half of the population got sick very fast, right at the beginning, then our line is starting here, let's say 2 is somewhere here. It's very hard for me to draw parallel lines, I'm going to try to do my best. You see, the fixed point moves to the right, and it's also a stable fixed point, but it is very big number. So if we vary the initial number of sick people, if we are able to reduce that at the beginning of the pandemic, so A is telling me about initial number of sick people compared to the total population. If we are going to reduce that, then we can reduce the overall casualties. Now let's look at, but notice, by changing the A, the number of fixed points are not changing, the quality of fixed points are not changing. So we definitely know that by changing A, there is no bifurcation happening here. Now let's vary B, let's keep A constant, and let's see what happens. And this is A. So let's make different, and B is always positive, so the line will always be downward facing. So one possibility is here. So here B is quite big, so this is B1. Then we have B2. Then we have B3. So notice one thing. When in case of B1, our fixed point is very much close to 0. So we have limited the total casualties, the stable fixed point of casualties. In B2 it's here, in B3 is here. Again we see that by varying B, there is no bifurcation happening here, but the total casualties, the stable, the fixed point, which is a stable fixed point, which tells me about the number of casualties to expect in the outbreak, we can reduce it greatly by changing the value of B. So let's look at B. So if you remember from the first slide, B is equal to L by K x naught. So B is equal to L by K x naught. So if I reduce B, if I'm reducing B, B3 here is less than B2, is less than B1. If I'm reducing B, I'm increasing the casualty. So let me correct myself. And if I increase B, I am reducing the total casualties. Okay. So let's say this is U star 1, U star 2, U star 3. The star is indicating this is a fixed point, stable fixed point, and 1 to 3 correspond to the corresponding B values. So B3 less than B2 less than B1, and the casualties look like this. So what I want to do is I want to increase the value of B. So to increase the value of B, one is to increase L. If L goes up, B goes up. The other is to reduce K. So I'm trying to minimize the damage, minimize the tragedy that the outbreak will cause. And one method is to stop the initial infections. And typically what happens is that after the initial infections have happened, the public health officials become aware of it because, First people will get sick, then people will start getting tested, and then they'll be like, oh, there's a dengue outbreak, oh, there is an HIV outbreak, or outbreak of other infectious diseases, or a plague, or some viral disease is spreading. So it's very hard to control A. Unless we know that the disease is coming, let's take some preemptive action so that we can reduce the overall casualties. For example, if we know that this is flu season, the flu is spreading, even before the flu season arrives, we can start taking precautions like hand sanitizers and masks to reduce the A. The other possibility is to increase B. So how to increase B? Increase the numerator, decrease the denominator. Sorry, decrease the denominator. Let's look at increasing the numerator. Increasing the numerator means increasing the fatality rate. Now this is tragic. No municipality, no country, no province wants this to happen because it's tragedy. We want to protect our people. So we don't want to increase the fatality rate. How would you increase fatality rate? By preventing medication and care, but that's very dangerous. Nobody wants to do it. So that's out of question. We are not going to play with L. We are going to reduce L. We are going to help as many people as we can. The other possibility is to reduce K. So now let's look at K. What was K? If you remember, dx by dt is equal to minus kxy. Every time a healthy susceptible person interacts with Y person, a fixed ratio of those interactions end up with the healthy person falling sick. So if we want to increase the value of B by reducing the value of K, we have to reduce the ratio at which healthy people fall sick due to their interaction with sick people. So this is where the genius of using masks, simple techniques, keeping distance. So if it's a disease that requires contact, we can avoid contact. So we can avoid touch, we can keep ourselves away from other people, so social distancing, physical distancing, and then the other is to wear masks. So in case of diseases that spread through the air we exhale and the air we inhale, we can use barriers. So if we use barriers, but how to reduce K? Use barriers. Second, physically distance. Third, to reduce K, sometimes using sanitizers and maintaining a certain level of hygiene will help. Now this depends on diseases. Different diseases require different kinds of reducing K. Now I did use the word dengue, but dengue does not spread from people to people directly. It's a vector-borne disease, so we need to modify this model, and I'll tell you briefly how to do it. So we can reduce K. So this is, I hope this explains why there was so much emphasis across the globe that we should use mask as a barrier, we should physically distance from each other, and we should use soap to wash our hands and keep our hands clean. Okay, students. So outbreak is going to happen, but if we can control the initial number of sick people, initial number of people who fall sick, or if we can increase the value of K by, of course we can't change the fatality rate, but by reducing the value of K, reducing the probability that there is a transmission of disease from healthy to sick people, we can reduce overall fatalities. Now what happens when we reduce overall fatalities? Okay, so this is the rate at which sick people are changing. If we can limit the Z, we are also changing the rate at which people are falling sick. And if we can limit Z, we can limit Y, we can also limit H because, number of healthy people, X. So basically, this is how our preventive measures come to prevent outbreak of diseases that spread with interaction between healthy and sick people. Okay, now let's look at our model and let's see how we can modify it for other diseases. So remember I told you that I will talk briefly about SIS model, SIR model. So these are very simple iterations of the same model. So let's go back to our very simple diagram that I drew. We have healthy people, we have infected or sick people, let's use the word I, and then we have people who don't make it, so people who die. So the model that we did today is healthy people falling sick due to interaction with interaction between healthy and sick people, and then a fixed proportion of sick people do not make it. This is what we studied. Now there's a model called SIS model. Now SIS model considers that healthy people are susceptible people. Here S stands for susceptible. Okay. Then they become infected. So I is the infected. And then once the infected people recover, so remember, infected people are recovering. Once they recover, they go back to becoming susceptible healthy people. So susceptible, infected, and then back to susceptible. So there is a inflow from infected people recovering, going back to H. So let's call it R. So sick people are recovering. So the healthy people population changes. Now it is minus KHI plus RI. So there's a rate at which healthy people are increasing plus RI. So this is how our system looks like. So when infected people recover, they don't have immunity. So this works for diseases when we know that healthy people, after they fall sick and then recover, they will lose their immunity. And we know that there are many diseases that happen, like there are certain kind of bacterial infection that affect us, where regardless of how many times we get them, we don't develop immunity. For many years, initially, there were certain other infectious diseases that plagued our world, and they still do, where immunity was non-existent even after recovering. So this is SIS model. So from susceptible to infected to susceptible. Then there is an SIR model. SIR model says that susceptible people, so healthy and susceptible people, they become infected and then they are recovered and immune. R is for recovered and immune. So how will I do that? Remove this. We were dealing with an SIR model. Once infected people recover, they are immune, they are not going to get sick again. And we saw this recently with our pandemic, that at least for initial few months, most people who recovered from the disease had pretty strong immunity against the pandemic disease, the viral disease. So that is SIR model, and the model we discussed is briefly SIR. But we can also make an SIS model. When a new disease spreads and the public health officials, the doctors do not know if the recovered personnel will have immunity, then we try to use both SIR and SIS model. Now, there's something else to look at. In the previous slide, what I shared was that if we increase the value of B, we can reduce total casualties, we can reduce the total number of sick people, we can also reduce the total number of people, total decline in the healthy population. So just by increasing the value of B, and B was L by Kx naught. So basically, reduce the initial rate at which infection is spreading, reduce the rate at which infection spreads when a healthy and sick people interact, or increase the fatality rate. We're definitely not going to increase the fatality rate. That is immoral, unethical. No country, no province wants to do it. But this gives us another insight into the way in which diseases spread. Look at B. All right. We know if B goes up, then casualties go down. The outbreak gets limited. We won't have a pandemic. We'll have a minor outbreak. We won't have an epidemic. So if you look at the nature of diseases in absence of intervention, so let's say I'm not intervening, I'm not asking people to physically distance themselves in case of a viral disease that spreads from aerosols, bioaerosols that we emit through exhalation. We are not wearing masks, we are not using barriers in case of other diseases, we are not keeping distance from sick, we are not isolating sick people. Then L and K in that case are nature of the disease itself. For example, there are diseases and like measles, K value is very high. So if a person who has measles goes around interacting with healthy and susceptible people, most of us are vaccinated against measles, which is good because it protects us from getting measles, protects people around us from getting measles. But the thing here is that if, let's say, there's a community where people do not have immunity against measles, and a sick measles person goes around interacting with them as usual, then the disease will spread very fast because the R naught of measles is very high. So the probability that a healthy sick interaction will end up with the healthy person falling sick is very high. Now, K also depends on socio-economic factors, social behavior. There are countries, and I'm going to name a country, let's say Sweden, where it is typical for strangers to maintain their distance. Like they don't even have to ask people to keep 6 feet distance. Culturally, they keep distance from each other. So in that case, the K will be different for them. K will be lower for them. In countries like India, where we don't have as much, we cannot afford as much physical distance in urban areas, and even in rural areas, we have definitely lower distance that we keep, lesser distance that we keep between two people compared to Sweden. So the K value here is going to be higher. Diseases are going to spread faster because of the interaction between humans and how frequently we meet people and how close we stand to them. And then there are countries where if somebody is sick, then the whole and even in our country, somebody is sick, then the relatives and the friends and the neighbors come to pay a visit. So what happens is that when the person is sick, even if they're not going out, the neighbors, the friends, the family, and the workplace friends, all of them come to visit. So in that case, the K goes very high. So K depends upon, of course, the nature of disease, but also depends upon the social behavior. So a disease that is spreading very fast in India may not spread very fast in a country like Sweden because the K might vary a lot. Sorry, not the K might vary a lot because the behavior of people changes. This is something that we saw with Ebola crisis in certain parts of the African continent, where people had very strong social ties. When somebody started developing symptoms, neighbors, the friends, the community came together to help them, to support them, and the disease spread very fast. So we know that depending on the culture, the denominator will vary. The other thing to look at is the numerator. Numerator is purely the function of disease in absence of interventions. So if there is a disease that has very high fatality rate, so let's say Ebola, very high fatality rate, what it means is that the B is going to be high, which means the disease is not going to spread as wide. That's why thankfully we have not had a pandemic of Ebola. On the other hand, the pandemic that we recently suffered, all of us globally suffered from, in that pandemic, the fatality rate was not very dramatic. So the disease, what happened was, since numerator was not very dramatic, the B value was not very dramatic. As a result, the fatality, the overall number of people we lost. So fatality rate is low. Fatality rate is low. K is high in the case of the disease that spread recently in our COVID-19 pandemic. K is high, fatality rate is low. As a result, what happened was that the B was very low. So we had a tragedy across the globe. We lost a lot of people. A lot of people fell sick. In fact, there are entire regions that people suspect that most people fell sick, got recovered, and now have natural immunity. So the disease spreads very fast. So just by looking at the value of B and knowing how when B varies, the number of people who we lose to the disease and number of people who fall sick varies, we understand that there are two scenarios. So one scenario is a disease has high fatality rate, and let's say the K value is low. So due to social behavior or due to the way the disease spreads. So measles is going to have very high probability that every interaction between a sick and healthy person ends up with healthy person falling sick. So in that case, the K will be high. So let's look at the second extreme. So when fatality rate is very high and K is low, the disease doesn't spread very easily and it almost always kills. In that case, what is going to happen is that we are going to have a very high B. B is going to be very high. So in this case, what's going to happen is that the disease is going to limit itself. U star is going to be small. So the overall fatality would be small, not many people will die, and the disease is going to die out. I think one example is Nipah virus that spread a few years ago in South India, Kerala. What happened was the fatality rate was very high and the government jumped in, made sure that the K remained low. The number of interactions remained low, and we did not see an epidemic of Nipah virus across the country. Very controlled, very well done. Let's look at another scenario. The fatality rate is low and the K is very high or decently high. What happens is that people, low percentage of infected people, 5%, 4%, 10%, people are not surviving the disease who fall sick. But people continue to interact with each other, they continue to spread diseases. What's going to happen is that your B is going to be low. Your B is going to go low. As a result, overall casualties would increase very high. So these are the two extremes, and of course then there is a whole gradient between these two extremes. Alrighty, now what I want to do is I want to look at the other way of approaching this problem. The method where we do not collapse the three-dimensional system into one-dimensional system, but we maintain two-dimensional system. We see the third dimension is not very important anyway, because if you go back to the equation, so we maintain the multidimensionality of our system and we do not reduce it to a 1D system. and we are going to use Nullclines, and we are going to sort of develop a phase portrait and sort of understand how the system works. Okay, so before we non-dimensionalize the system, it looked like this. Dx by dt is equal to minus kxy, sick people, infected people, and then people who don't survive the infection. So notice here, the first two equations don't have z in them. They don't have the number of dead people in them. So we can say that this is sort of not affecting the first two equations. It's not affecting dx by dt and dy by dt. So we can say this is a 3D system, but we can treat it like a 2D system, right? So now we have dx by dt is equal to minus kxy, dy by dt is equal to kxy minus ly. Now if you remember how to solve a 2D nonlinear system, I asked you, first step is to find the fixed point, the second step is to write a Jacobian. So Jacobian here, so we can approach the Jacobian way. Now to write the Jacobian, we take the first equation dx by dt and we differentiate it partially with respect to x, we will get minus ky, and then we differentiate it partially with respect to y, minus kx, and then we repeat the same thing here. So this is our Jacobian that we'll get. Now we want to find the fixed points. So for fixed points, both dx by dt and dy by dt should be equal to 0, right? And then the fixed point, and then once we find our fixed point, we can substitute it to a Jacobian, get a characteristic equation, and find out the trace and determinant. Oh, cool. This is another way of approaching this, and that's the Nullcline method. And since we have not dwelled a lot on the Nullcline method, I want to take few minutes to talk about the Nullcline method. So Nullcline method, we do one thing. We make our, instead of running directly into phase portrait, we'll draw a 2D diagram, and I like to use Nullcline methods for only 1D and 2D systems. That's where they work. They're easier to work with. So this is a 2D system, perfect. What we are going to draw is, instead of finding a fixed points and then the Jacobian and then the characteristic equation and then the stability, what we are going to do is we are going to draw two Nullclines. So there are two Nullclines. In 1D system we had only one Nullcline. The first Nullcline is when dx by dt is equal to 0. So this is the Nullcline at x. It is when dx by dt equal to 0. So now here we have minus kxy equal to 0. When will minus kxy equal to 0? They will equal to 0 when either x is equal to 0 or y equal to 0. So let me use another color for this. So the x Nullcline when dx by dt is equal to 0 is when x is equal to 0. So we have here, and then when y is equal to 0. So we have here. Okay, the y Nullcline, let's use another color for this, is when dy by dt is equal to 0. So obviously you can see when these two Nullclines intersect is where we get fixed point, because in that situation both dx by dt and dy by dt are going to be 0. Okay, so dy by dt 0 is when kxy minus ly is equal to 0, which is y, kx minus l is equal to 0, which is when y is equal to 0 and or when x is equal to l by k. So let's draw this. So when y is equal to 0, so we have here, and then we have x is equal to l by k. Okay, so these are the two Nullclines, one is in red, one is in green. Now by definition, when dx by dt is equal to 0, by definition the flow will be vertical. So as we approach this situation, the x Nullcline, the flow will be vertical. So we are going either top bottom or bottom top. And when dy by dt is equal to 0, which is the y Nullcline, the flow is going to be horizontal. So let's look at the y Nullcline. So these green lines are the y Nullcline. And on the right side of this Nullcline, here we have x greater than l by k, and we have y greater than 0. Here we have x greater than l by k, y less than 0. Here we have x less than l by k, x less than l by k, and y greater than 0, y less than 0, y greater than 0. Okay, So on the right side of this green line, we see that x is bigger than L by k. And in the first quadrant here, first quadrant related to this, in this area, y is also positive. So what's going to happen is dx by dt is going to be negative. So here we know that I'm going to use x dot to show dx by dt is negative. So x dot is less than 0. Let's look at dy by dt. Now dy by dt is equal to y into kx minus L. X is more than L by k, y is positive, so dy by dt is going to be positive. So in this particular area, what's going to happen is x is dx by dt is negative, so x is going to reduce, y is going to increase. So x is going to reduce, so movement is going to happen from right side to left side, y is going to increase, so from bottom to top. So the flow here looks like this. The flow lines look like this. Now in the bottom quadrant here, let's look at this. X is bigger than L by k, y is less than 0. So dx by dt is going to be negative. So here dx by dt is going to be less than 0. Let's look at dy by dt. Now y is negative, this is going to be positive, positive, negative. Dy by dt is also going to be less than 0. Both are going to reduce. So the flow is going to be in this direction. Now let's look at this area, and I'm going to highlight it, looking at this area. Okay, so let's go back to the previous quadrant. Okay, x is greater than L by k, y is less than 0. So dx by dt is equal to minus kxy. X is positive, y is negative. So dx by dt is going to be positive. Now in this case, y is negative, this is going to be positive, dy by dt is going to be this. So what's going to happen is x is going to increase, y is going to decrease. So we're moving in this direction, opposite direction. So we're moving like this. But here's the thing, since y is never going to be negative, we don't even have to worry. So let's go back to our yellow quadrant. So in the yellow quadrant, x is less than L by k, y is greater than 0. So y is greater than 0, y is positive. We are looking at dx by dt first. And x is also positive, so x is going to reduce. So dx by dt is going to be less than 0. Now let's look at y, rate at which y is changing. This is going to be negative, this is going to be positive, so y is going to reduce too. So both are going down. So what we'll have a situation is that the flow will look like this. To use another color, the flow is going to be like this. Okay, we'll continue our discussion of nullclines in the next lecture, where I'll show you how to interpret this result. So now let's look at the yellow highlighted portion. So in the yellow highlighted portion, what's happening is that x is less than L by k, y is greater than 0, y is positive, and remember dx by dt is equal to minus kxy. So x is positive, y is positive, so dx by dt is going to be negative. Dx by dt is going to be negative. Now let's look at dy by dt, kxy minus ly. Now in this situation, since x is less than L by k, this portion is going to be negative, y is positive, so the product is going to be negative, so y is also going to reduce. So we have y also less than 0. So what we'll see is that the overall flow in this quadrant will be here. Okay, in the next lecture I'm going to continue this nullcline discussion, and I'm going to show you how to interpret the results, how we look at these flow lines to understand where the fixed points are. Now I already told you the flow line, the fixed point will be at the intersection of the two nullclines, which is here, and then by looking at the flow we can understand whether it's a stable fixed point or an unstable fixed point. All that for the next lecture. See you there. Thank you.